to do that, we're going to reassociate this append. B append utter, quantity append fly. Well, append should be associative. There's a theorem that append is associative. You've probably proved this theorem already if you did the homework. So let's use it. We'll rewrite by the theorem twice, once on the left up there and once on the right. Now, let's remind ourselves about the transitivity of the permutation relation, right? If L is a permutation of L prime and L prime is a permutation of L double prime, then L is a permutation of L double prime. So let's apply the perm-trans rule with this intermediate permutation. So now we have two proof goals. And here we'll again rewrite by the associativity of append, in particular with utter and fly. So you can see what that's doing. It's re-parenthesizing right up here. Okay. If I have L appended with L prime, that's a permutation of L prime appended with L. That's a theorem proved somewhere in the library by induction, which is how we prove things. So let's apply this, because in fact, we have that case. We have utter fly here, we have B here, we have utter fly here, we have B here. Okay, now we've brought utter to the front on one side. We'll do the same set of operations to bring utter to the front on the other side. And now we have utter concatenated with some stuff is supposed to be a permutation of utter concatenated with some other stuff. So we can search for theorems about permutation of concatenations, and this is the one we want, permutation app head, which says if you have L at the front of two things, it sort of can be canceled out, that as long as the tail and tail prime are permutations. So we apply permutation app head, and this is our remaining proof goal. Okay, so let's swap this append around to bring FL before BY. And so we'll do E apply perm trans. What does E apply do? It says, let's put in a unification variable called question mark L prime that will be instantiated by whatever lemma application we do next. We could have used just apply. If we use just apply, then we would have to write by hand what's the intermediate term. That would work, but this is easier. Okay, because we can just swap this around. In proof goal 2, so that's the 2 colon, let's apply permutation app com. And that will instantiate L prime over here with FL append BY. But instantiating the unification variable here also has the effect of instantiating it here. So bingo. All right, let's simplify that. FLYB and FLBY. So remember perm skip, which says if L is a permutation of L prime, then X cons L is a permutation of X cons L prime. So let's apply that twice. Bonk, bonk. And now we can apply perm swap. Okay. Can you remember all the names of those permutation lemmas? No. That's why we have the search command. All right. Here's the homework, part 1. Prove that this is a permutation of that. And you should be able to do this in 5 minutes using these 4 permutation lemmas. Basically using the same method. All right. In my description of what's a permutation, I said, well, we can gain confidence in that permutation is the right inductive definition because all these things are true. But actually, if we had defined permutation AB colon equals true, then all those things would be true. We would like to know that some things aren't permutations of each other. That could also help us gain confidence that this is the right definition. So here's a theorem you can do in the homework. 1, 1 is not a permutation of 1, 2. Not too hard to prove. And you would gain confidence that this might actually be the right definition of permutations. Okay. So maybe swap. Remember maybe swap? It's a little sorting algorithm. It sorts at least the first 2 elements of the list. And so it should satisfy this requirement we have for sorting algorithms, which is that its output is a permutation of its input. So let's prove it. Oops. How do we prove it? Let's remember what maybe swap does. So we'll just print it right here. If AL is nil, return AL. If AL is a singleton list, return AL. And if AL is 2 elements, do something else. So we should do case analysis on whether AL is nil. How do you do case analysis on whether AL is nil? Destruct AL. So let's do that. And how do we prove this? Well, first of all, let's simplify it. And then, if we're lucky, this is the name of the lemma. We're lucky. Okay, if we're not lucky and that is not the name of the lemma, how do we prove it? Well, then we do a search. Yes?
Would constructor also work here?
Would constructor also work here? It does work here. So if we're lucky, we remember which things in the permutation theory are primitive as part of the definition of the inductive relation and which are derived. But in the long run, I don't want to have to remember that either. So, okay, here's the other case. And we could do the search about and the so on, but I believe perm skip is what we want to apply here. No, it isn't, because that's a maybe swap in the way. So let's simplify this. Simplifying this shows us the rest of the case analysis in maybe swap. So once again, we've got to destruct AL, and then in each case simplify. How do we prove this? Well, the reflexivity of permutation would do, but I don't think it's called this. It's called this. Oops. For no very good reason. Now what? Are we done? We have to do case analysis. How do we do this case analysis? We're going to do a B destruct. Of n0 less than question mark n. So now we have 2 cases. Notice that the H hypothesis above the line is not actually useful in proving whether it's a permutation. It's only useful in proving whether it's increasing. We don't care whether it's increasing. Ordinary destruct would have worked just as well for this particular theorem. All right. Check perm swap. Perm swap looks very useful here. So let's apply it. Okay, and this is just permutation REFL. So that was easy. Here's another part of the correctness specification of maybe swap, right? Let's define first less than or equal to second about a list is that if it has at least 2 elements, the first element is less than or equal to the second element. And that's the sort of increasing property that maybe swap guarantees us. And this is not supposed to be here. Okay, so let's prove this. And it must be, again, by destruct of AL. And then in each case, simplify. Well, I think I know how to prove that. Auto is a good way to prove that. Now, here again, we need to destruct AL. You can get a hint about what to do next by just looking at there's a pattern match. And part of success in coq verification is not thinking too hard, right? If you see some, well, for example, if you see a for all, and the easiest thing to do is say intros. Intros is not always the best thing to do, but usually it's the best thing to do. And it's easier to just say intros and correct later if that wasn't the best thing to do, right? So by that method, if you see a pattern match on AL, let's just destruct it. And in each case, simplify. Well, what happened here? We simplified away this case of first LE second, basically. And so, again, we just get true, which is easy to prove. And now, what do we do next? We do a B destruct on n0 less than question mark n. And here, and in each case, let's simplify. All right, so this is easy. The thing we got from the B destruct is exactly our proof obligation. No, it isn't. It's stronger than our proof well, yes. So how do we prove that less than implies less than or equal to? Omega. We used the theory of linear integer arithmetic. If you thought that there was a simpler way, you're right. But if you thought there was an easier way, you're wrong. Okay. Now, how do we prove that less than or equal is the opposite of greater than or equal? Omega. All right. So, do the little homeworks in perm.v. They won't take long. And now let's talk about sorting. I showed you insertion sort. If you have to use a simple sorting algorithm on not too many elements, insertion sort is a very good algorithm. It's efficient. It's easy to verify. Another algorithm you could use is selection sort. How does selection sort work? You walk through all of the elements, finding the smallest one, and you pick it out and you put it over here. And then you walk through all the remaining elements, finding the smallest one, and you pick it out and you put it over there to the right of that one. And you do that, and each time the remaining elements is a smaller and smaller list. So it also takes time, something like n times n minus 1 over 2. But in practice, it's slower than insertion sort. Well, unless for some reason moving elements is very expensive compared to comparing them. Like if I have to rearrange all the heavy boxes in a warehouse, I might think about where they go first and then move each box only once. Okay? But for most purposes, selection sort is slower, it's more complicated, it's harder to implement, it's harder to verify. There is no good reason to use selection sort except one, which is I'm going to demonstrate here the proof of selection sort, and you can do insertion sort for the homework, which is easier. Okay? Instead of vice versa. So I'm going to go ahead and do the verification of selection sort, but you should understand that when this looks hard, it's because it is sort of hard, and that the homework you have to do is much easier, and you really should be able to do this homework this afternoon in the homework period. And I strongly encourage you to do the insertion sort homework because it will prepare you for tomorrow and next week when we do other more sophisticated things in coq. All right, so how do we find the smallest element in a list? Well, here we go, the select function. The list has to be at least length 1, otherwise it doesn't have a smallest element. So the way we're going to organize select is the list is really x cons L, right? But we'll just separate out the first element from the list. So we're really finding the smallest element in x cons L. And that will return the smallest element and a list of all the other elements, not including the smallest one. Okay? So if L is nil, then the smallest element of x cons L is x, and the rest of the elements is nil. But if it's h cons t, then if x is less than or equal to h, then first select the smallest element in x cons t. Suppose that's j, and suppose the rest of the elements in x cons t are L prime. Well, we know that h is bigger than x, and j is at least as small as x, so therefore the smallest element in the whole list has got to be j, and we can put h back on the front of L prime. Okay, but suppose h is greater than, x is greater than h. So now x can't be the smallest element. H is a candidate for being the smallest element. So let's find the smallest element in h cons t, call that one j. L prime is the rest of the elements in h cons t. And now j is the smallest element overall, and x cons L prime is the rest of the elements. So that's select. Now, here is selection sort. It's if L is I cons R, then we can do select on IR, right? So find the smallest element in I cons R, call it J. The rest of the elements is R prime. So let's cons J on the front. It is the smallest element in the resulting list. And then do cell sort recursively on R prime. So that's selection sort. And coq is complaining. What's coq complaining about? The recursive call to cell sort has principal argument equal to R prime instead of R. Okay, what does that mean? When we write fixed point functions in coq, the recursive calls have to be on the immediate substructural children of the formal parameter L. So we can do a recursive call on R, but we're not allowed to do a recursive call on R prime, right? Because R prime is not structural. A structural, it's a substructure of the immediate, of the original argument. All functions in coq must be total. And that's the way coq enforces it for fixed point functions in particular. Now, why must all functions in coq be total? Suppose I have a square root function on the integers. And, or better yet, on the natural numbers. I have a square root function on the natural numbers, and I have a theorem that square root of n times square root of n equals n. And I say square root of 2. Well, square root of 2 has type nat, right? This hypothetical function. And therefore, square root of 2 times square root of 2 equals 2. There's a contradiction here, and pretty soon we'll be able to prove false. So, in order that we can, when we write f of x, we want to say that's actually a value that we can substitute for things. Right? The logic works well because when we say f of x actually exists. So to make the logic work well, we want f to be a total function. In coq, you can only define total functions. So that's the reason. And then fixed point has this simple rule for proving to itself that the function